Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the reverse biasing of the PN junction diode. So obviously in the reverse biasing, we would be connecting the P side of the diode with negative terminal of the battery and N side of the diode with positive terminal of the battery. So this is the connection of PN junction diode. And now in P side you can see that obviously external electric field is in support to the barrier electric field, and the net electric field in the depletion region is greater than the barrier electric field because it is supporting the barrier electric field. Now, as external electric field is supporting the barrier electric field, the diffusion current does not flows in this case, and drift current flows in this case, which means that this external electric field pulls these holes away from the junction and these electrons away from the junction. So it is not encouraging the diffusion current to flow through the junction. In fact, it pulls these electrons on the P side, which are the minority carriers, towards the junction, and these holes on the N side, which is the minority carriers, towards the junction. So this external electric field is supporting the drift current, and as you know, the drift current is due to the minority carriers. So the value of the amount of minority carriers in P side and N side is very small. So the diffusion, the drift current will be very small, which would be flowing, and the junction is being this depletion region width is increasing in the reverse biasing due to the fact that external field is supporting the barrier field. Therefore the junction resistance in the reverse biasing increases to very high amount, and it ranges around from 50,000 to 5 mega ohms in reverse biasing. And due to this high resistance and due to the low availability of the charge carriers, which is the minority charge carriers, the current flowing in the reverse biasing is very small, and therefore we can say that the current in the reverse biasing remains almost constant, and it is of order of microamperes. So this is the connection. Now let us discuss another thing, that I've already written these things in this page. You can take the screenshot, and this is very important to note that width of depletion region increases in the reverse biasing. Now it is very important that when we know that there are the reverse current in the reverse current flowing in the reverse biasing is constant due to the fact that the number of electrons or holes which are the minority carriers are fixed in the diode. So the reverse current would be constant and would be independent of the voltage applied, because if you are increasing the voltage, the number of electron holes which are in minority are already flowing through the junction, so there would be no extra electrons and holes available for current. So reverse saturation current will be constant and independent of the voltage applied, reverse voltage applied. And obviously at some constant temperature, the electrons holes are getting created due to thermal agitation, and the rate of creation of electrons and holes at constant temperature is fixed, and therefore we can say that at constant temperature in reverse biasing, the current flowing through the PN junction diode is constant and is called as reverse saturation current. Now, if we increase the temperature eventually in reverse biasing, then we can say that the rate of generation of minority carriers will increase, and therefore the drift current will be changing, and we can say that the reverse saturation current will be increasing. Okay, and this is the first case. Second case is the fact that if we are increasing the minority charge carriers by some other way, we are increasing the number of minority carriers by making the photons of sufficient energy incident on the diode, which is the case in photodiode. We would be studying the photodiode later on. So in that case, due to the energy of photons, more electron hole pairs are generated, and the reverse saturation current is increasing in that case. So this current is due to the minority carriers, and in silicon it is of order of nanoamperes, and in germanium it is of order of microamperes. This I have already told that the resistance offered by the PN junction diode in the reverse biasing is of order of 5000 ohms to 5 mega ohms. Now, see, this is a very important thing to note, that we know that the junction offers a very high resistance in PN junction diode in reverse biasing, and the P region and N region offers a comparatively low resistance in the reverse biasing. So we can say that there is a high resistance region, which is the depletion region, and this region is sandwiched between two low resistance regions. So this region acts as a parallel plate capacitor, and P side and N side, like that I'll show you that this region is of high resistance, this region of high resistance, and these are of low resistance region. This is low resistance, this is low resistance. So there is a parallel plate capacitor which is formed, whose plates are this and this, and this depletion region acts as the dielectric for this capacitor. This capacitance is also called as junction capacitance or transition capacitance of the PN junction diode. Okay, so this is in reverse biasing, PN junction diode is acting like a capacitor. Now we know that obviously when the diode, there are two effects in the diode. First is reverse breakdown, and second is avalanche breakdown. So we know that if we keep on increasing the reverse voltage, then obviously the current will become constant, because the minority charge carriers are fixed in the amount. So current flowing through the diode will be constant, and this constant current is known as the reverse saturation current, and it is independent of the applied voltage. But a time comes when the voltage is very high, in such a way such that more and more electron and holes will be created in the diode due to the high voltage, and diode crystal will break down, and many electrons and holes will be created in the diode. So this is called as reverse breakdown, and after reverse breakdown, a high current will be flowing through the diode. And if this current is not damaging the diode, we can recover the diode to its original state by decreasing the voltage. But if this diode is getting permanently damaged due to Joule's heating, we could not recover this diode in the original state. Now there is another effect which is called as avalanche breakdown. So after reverse breakdown, in which many charge carriers are created due to high voltage, when these charge carriers are pulled towards the junction or pushed away from the junction to flow the current, a heavy current flows through the diode, and this heavy current produces a very high kinetic energy in the charge carriers, and those fast moving charge carriers knocks out more electrons from the covalent bonds, and more electron and hole pairs are generated. Those extra generated electron hole pairs are also now moving with a very fast velocity, and those charge carriers again knocks out some more electrons, and this is a chain reaction which gets started in the diode, and a very large amount of current flows through the diode, which burns the diode permanently. This is called as avalanche breakdown. So avalanche breakdown comes after the reverse breakdown, and we cannot recover the diode after avalanche breakdown. We can only recover the diode after reverse breakdown. So it is very important to note that these two phenomena are different. So this is the VI characteristic of PN junction diode, and you can see that we have already discussed that at a constant temperature the rate of generation of minority carriers will be fixed, and therefore the rate of flow of minority carriers through the diode junction will be fixed, and therefore reverse saturation current will be fixed, and it would be independent of applied voltage. But but at a point which is at a voltage which is called as reverse breakdown voltage. After this voltage, this diode gets breakdown, and due to that reverse breakdown, a huge amount of current flows through the diode, and due to that huge amount of current, more electrons are being knocked out from the diode, and avalanche occurs in which many charge carriers are flowing in very high speed from the diode, and those charge carriers are knocking out more and more electrons, and chain reaction starts to occur in the diode. So this is a very important concept, and diode could not be recovered after avalanche breakdown. Now reverse saturation current for silicon diode is around 0.02 microampere, and reverse saturation current for germanium diode is around 0.05 microampere. It is slightly greater for germanium diode is due to the fact that the forbidden energy gap in germanium diode is less than the forbidden energy gap for silicon diode. So it is easier for covalent electrons to jump from valence band to conduction band in germanium diode. So availability of minority charge carriers at a constant temperature is higher in germanium diode, and it is lower in silicon diode. So therefore, the reverse saturation current for germanium diode is greater than the reverse saturation current for silicon diode. So this was the VI characteristic of reverse biasing PN junction diode. And let me also tell you that the resistance offered by the PN junction diode in reverse biasing is of very high order, and it is of around 50,000 to 5 mega ohms. So this is the reverse biased PN junction diode. Thank you. Now we will be also discussing this current in the reverse and forward biasing. So let us discuss this current in detail. So we know that in reverse biasing, V is negative. V is negative because it is reverse biased voltage, and the value of V is very high. So we can say that this e to the power minus V upon neta k t e is very less than 1. Okay, because V is very high. So it is very less than 1, therefore I will be equal to I naught for this reverse biased PN junction diode, and I naught is the reverse saturation current, and this is minus I naught obviously because the value of current will be equal to reverse saturation current, and negative shows that this current will be flowing in the opposite direction. And in forward biasing, we can say that V is positive, and the current in the circuit grows exponentially like that. And if V is greater, very greater in forward biasing, then we can ignore this one if this quantity is very greater than 1. So in forward biasing, this is the current flowing through the diode, and in reverse biasing, this is the current flowing through the diode. So this was the current analysis of the forward and reverse biasing. Thank you.